So please introduce yourselves and briefly summarize your education and professional backgrounds.
I'm Stuart Rankin. I'm a senior vice president at WSP USA. I'm in the National Bridges and Structures practice. I've been with WSP since 1996, so that's coming up on 30 years. My tenure with the company started when we were known as Alman and Whitney Consulting Engineers here in New York City. We were then acquired by Lewis Berger, which was then acquired by WSP, which is how we got to be WSP today. I went to undergraduate at Lehigh University in Bethlehem, Pennsylvania, graduated in 1991, and then I got my master's in structural engineering from Rutgers University in New Jersey. I'm a professional engineer with registration in probably more states than I care to count. Jonathan, how about you?
My name is Jonathan Morey. I went to the University of Maryland at College Park. That's where I got my bachelor's in civil engineering. After that, I started off and work at STV for 5 years. And then I moved over to Alman and Whitney, which then, as Stuart indicated, became Lewis Berger and then WSP. So I've been working with Stuart on suspension bridges since 2009. It's been extremely interesting, and I've been very fortunate to be included in many of the main cable dehumidification projects, which is kind of a niche project type for suspension bridge cable preservation.
All right, so speaking of decadal anniversaries, we're here to talk about the Verrazzano-Narrows Bridge, which crosses from the Brooklyn to Staten Island, and it turns 60 on November 21st. Now, I have a decent amount of background information, including its origins within WSP, but can you describe why you think this is such an important bridge in terms of historical significance?
Like most bridges, it's connecting communities. Prior to the construction of the bridge, Staten Island was somewhat isolated. It definitely had no direct link with the neighboring borough of Brooklyn. So the ability to connect communities, which results in enabling increased commerce, increased ease of commuting for people to get to work. It really allowed the development of Staten Island as a residential area for people working in other boroughs of New York City.
I think just from the aspect of the sheer size of the bridge, as well as the foresight that was put into the planning of the structure itself so that it would last this long without major modifications to its ability to carry the traffic flow, says a lot about the engineers at the time and their forward thinking.
Just as a little bit of background information, you can fact check me. I believe that the Verrazzano-Narrows Bridge name comes from Verrazzano was the first person to sail to the New York City area, and that the Narrows is just kind of the narrowest part where the shortest distance between Staten Island and Brooklyn. Is that correct?
Yes, that's correct. So Narrows does refer to the narrow width of the waterway, and you are correct on the naming. And I'm just trying to grab his, Jonathan, and you can also search online if you can. I'm trying to grab his first name that the bridge was named after. The Italian immigrant. I'm just trying to find his name.
No, it's okay. I believe I found that somewhere. And that was Giovanni da Verrazzano in 1524.
Correct. So yes, and the naming of the bridge was not intended to be named after him initially. Like many bridges, they're often named based on the waterway they go over. So the bridge originally was anticipated just to be called the Narrows Bridge. But then as the bridge got further along, becoming more and more of a reality, that's when they decided to dedicate the bridge and name it after him.
Okay, and this was designed by famed engineer Othmar Aman. Did I get that right?
You did, Othmar Amen.
Othmar,
And
okay, thank you.
as you heard Jonathan and I say in our introductions, we initially started in this field working for Amen and Whitney. So yes, the Amen, as in Othmar Amen, the world-renowned suspension bridge engineer, he got together with Charles Whitney, who was very much a buildings and blast and more conventional structural engineer. Othmar Amen, Charles Whitney got together to form Amen and Whitney. But yes, the bridge was designed by Othmar Amen.
Okay, a couple other details I'm hoping you can help me out with a little bit. I read that it had an innovative truss system for its time, and that it also accounted for the curvature of the Earth. Do you mind explaining those to me a little bit?
Yeah, Jonathan, I can take either one of those topics. Is there either one you'd prefer to take?
I'll take the curvature of the Earth for 200.
Go for it.
Due to the distance between the towers, the main span of 4,260 feet, the to be plumb vertical at that distance, the distance between the tops of the towers would have to be approximately 2 inches apart. So from the first tower to the second tower, the tower bases are 2 inches closer together than the tower tops are.
And regarding the truss, and I might butcher the name, but it's the viendril truss. And a viendril truss is different than a traditional triangulated truss, for lack of a better word, in that traditional trusses, as I said, triangulated truss, is built up of a series of vertical, horizontal, and diagonal members. The viendril truss for Verrazzano only consists of horizontal and vertical members rigidly connected together. That causes the members to have to carry a combination of bending, shear, direct stresses. Traditional trusses, usually the members act in compression or tension only axial forces. The viendril truss is underneath the structure. Along the side of the structure, there are two stiffening trusses. Those two stiffening trusses are traditional triangulated trusses with diagonals. Connecting one truss to the other truss, in essence, the floor system underneath the bridge is a viendril truss. If you've ever driven the lower level of the Verrazzano-Narrows, essentially you're driving through the trusses. All you see from the lower level is a vertical post at the center line of the bridge. It's that vertical post that is part of this viendril truss system. Typically, underneath a suspension bridge roadway, you would have one of two things. You could either just have floor beams that go transverse to the bridge, or you would have what we would call a floor truss system that goes transverse to the roadway. A floor truss system would not work if you wanted to put a lower level on because of all the diagonals that would get in the way. To have a lower level, you need to get all those diagonals out of there to open up the space to put a roadway in. And that is accomplished via the use of this viendril truss, which has no diagonals.
All right, those are great descriptions, but were these novel ideas and concepts at the time, or were these kind of understood ideas? I know this is the longest bridge of its type at the time, so maybe they didn't have to deal with Earth curvature at the time, or was this something that was kind of established 60 years ago?
Regarding the curvature of the Earth, that was established years ago, but it wasn't accounted for many times due to the magnitude. There's a tolerance in construction that often is easy to overcome fractions of an inch. So when you're dealing with smaller spans, it doesn't need to be taken into account quite so with such a level of intricacy. But when you have such a large span, the details matter. So you need to work it down to the fractions of an inch. Regarding the truss I think there were many levels of understanding gained from the failure of the Tacoma Narrows Bridge, especially in relation to the ratio of the deck width to depth. And so the stiffness, the transverse stiffness, and the aerodynamic considerations that the new truss approach uh, or application for the Verrazzano-Narrows Bridge, that was an innovative factor in that it overcame concerns that were raised following the loss of the Tacoma Narrows deck.
A vierendeel truss was the first vierendeel truss, I believe, was designed in the late 1800s, probably constructed in the early 1900s. The design was by Arthur Vierendeel, therefore named after him. So while that concept of a vierendeel truss was a well-known structural configuration, what made it innovative was its use on a suspension bridge. I believe that the use of the vierendeel truss on the Verrazzano-Narrows was the first utilization of that type of truss on a suspension bridge, at least here in North America.
All right, that's great. That's just kind of information I was looking for. So jumping forward in time, I believe there was a major redesign that WSP worked on or led that just completed in 2023. Is that correct?
One was um, a project that we had a little bit lesser of a role in. It was the upper level deck replacement. They took off the original deck, put on a new steel orthotropic deck, and it allowed for the addition of a reversible center lane so that they could have a dedicated bus lane on the upper level via the use of a movable barrier system. The other project we were involved with was a reconfiguration of the ramps on the Brooklyn side. Again, it's great when you can have a new bus lane on the upper level, but when the existing ramps were set up to handle the original dedicated lanes in each direction, now to have the reversible lanes, it really requires a reconstruction of the approach ramps, anchorage transitions from the suspension bridge to the ramps. So there's been quite a bit of reconstruction of the ramp system on the Brooklyn side.
Can you tell me a little bit more about the steel orthotropic deck and how what kind of exactly that is and why what was different about it from previous original 60-year-old deck?
So in general, a orthotropic deck consists of a flat steel plate as the horizontal decking surface. It is stiffened by U-shaped troughs. I use the term U-shaped troughs loosely. I might want to say trapezoidal shaped troughs underneath the deck plate, and they serve to stiffen the deck plate as well as provide a means to connect the orthotropic deck system to the structural supports below. The orthotropic deck steel plate is then overlaid with an asphalt wearing surface that the vehicles drive on. Orthotropic deck compared to the original deck on the bridge, which was a concrete deck, has advantages such as much lighter weight. As you can imagine, a concrete deck slab is quite heavy. An orthotropic deck can be designed to be lighter than the original concrete deck. Certain aspects of a orthotropic deck are challenging and have to be detailed correctly. Orthotropic decks, if not detailed correctly, tend to have fatigue issues at some of the complex intersections between all of these steel members, the steel deck plate, the steel supporting ribs below. So there has to be a lot of trial and error with the design, iterative design, testing of panels. So again, for the orthotropic deck on the upper level, prototype panels were actually tested to confirm the details to ensure that it was not a fatigue-prone deck.
So how was the bridge redesign, besides just what we talked about, different? Has it changed much since its original version 60 years ago in terms of like length, size, and capacity?
Length and size, the short answer is no. It's really, really hard to say lengthen a suspension bridge, just due to the physical constraints of towers and anchorages like that. As far as capacity, I just alluded to with the upper level redecking. They did add an additional lane to the upper level by taking out the original median that allowed for this reversible bus lane. So that's capacity. Also, like I said, orthotropic deck is lighter than a concrete deck, so that also goes to increased load carrying capacity of a bridge. So there are some ways to increase the capacity of a suspension bridge, which have been done on the Verrazzano-Narrows. But again, the overall dimensions of the length of the main span between towers or length of bridge anchorage to anchorage, and as well as the width of the bridge remain original. Jonathan, anything else on that topic?
There's not much to add there other than the majority of the work has been on making the most effective use of the available space and improving the approach access to that space.
And there were some modernizations too, right? Like tolling, lighting, things along those lines.
Sure. The Verrazzano-Narrows has a long history of a variety of different type of tolling configurations. Over the course of its lifespan, tolling has gone through several iterations where tolling would only be in one direction, or at other points in its time, you'd pay the toll in each direction. The toll in each direction was half, as opposed to when they had tolling only in one direction, where the toll would be doubled. A lot of things go into that. Queue times, traffic flows, the amount of time vehicles sit in traffic, and what kind of impact that has to the environment of all the vehicles sitting at the toll plaza. So currently at the Verrazzano-Narrows, they have an open road tolling system. They have gantries that go over the roadway, and so the vehicles never slow down. They continue at high speed, and whether you have an easy pass transponder or it reads your license plate, there's a variety of ways that they collect their tolls, but they no longer have the old style toll booths with gate. It's now all at highway speed tolling.
I now want to cover a little bit about bridge inspections because I believe WSP has been doing the bridge inspections for this approximately entire 60 years.
The bridge owner, the Tri-Borough Bridge and Tunnel Authority, hires different consultants to do their biennial inspections. And yes, WSP has regularly done the biennial inspections of the bridge. Not every year or every other year for the life of the bridge, but it's a competitive basis that the TBTA hires their inspection consultants on, and I'm happy to say that WSP is fairly frequently the selected consultant to do the biennial inspections on the bridge. Was there something specific you were curious about the inspections?
Yeah, I'm curious to know how much inspections add to like any bridge's lifespan, or maybe particularly this bridge's lifespan, and what role the inspections played on deciding that it needed redesign.
Routine inspections are vital to every bridge's operation. Adding to the lifespan of the bridge, routine inspections are critical because they identify routine maintenance issues. They identify special circumstances that might be arising. They identify these things in advance of them becoming critical. They allow for the systematic and programmatic ways to repair things, rehabilitate things as they're discovered. Since the bridge is inspected every 2 years, it allows a great way to track deterioration as it is occurring on the bridge, to allow the bridge owner to most effectively use their limited funding, their limited budgets, to repair what's needed when it's needed, so they're not wasting their money repairing things too early or repairing things that are unnecessary. So for the Verrazzano, again, you mentioned the upper level deck. Obviously, the concrete deck was being tracked. The condition of the concrete deck was being tracked through these biennial inspections. Maintenance efforts were being tracked by the bridge owner to determine how much money they were spending on minor repairs to the deck. All of those elements, the rate of deterioration, the rate of spending of repairs, that all gets factored into the decision-making process as to when the right time to replace the deck is. All of that starts with these routine biennial inspections.
Yeah, adding to that, there are some special inspections that take place as part of the special elements that make up a suspension bridge. The main cables receive internal inspections on varying frequency based on the observations of the previous inspection. And then there's also suspender ropes, which are the vertical ropes connecting the main cables to the stiffening truss. Those are inspected to make sure both the condition as well as the actual force at which they would break well exceeds the demand load. So by having a better understanding of the actual capacity of the cable, which is based on statistical application of what is observed during these specialized inspections, we can understand what the capacity of the cable is and then model what the demand is on the cable and use that to determine the approximate safety factor so that we can make recommendations to the authority on future plans to maintain the bridge in a good service life.
All right, so to kind of sum it up, as this historical bridge is about to turn 60, what kind of impact would you say it has had on, let's say, bridge engineering, perhaps engineering in general, and maybe even in your own professional careers?
When the bridge was designed, when the bridge was built, the longest span in the world, it really pushed the use of the materials to its limit. As the bridge was designed, as older bridges were designed, there was a lot more conservatism in the designs, a lot more fat, if you will. Verrazzano was right on that cusp of the cutting edge where technology and I'll use the word computers, but computer back then was different than what we have now. But computer-based design, it was in its infancy, but it really started to take hold around that time in the early 60s. So design was focusing more on optimization and more efficient use of materials. We had higher levels of confidence in our calculations. As any engineer will tell you, there are a lot of assumptions that go into calculations and design. And we were able to, the industry was able to refine those assumptions to come up with a more efficient design. As far as the bridge and me personally, you really touched on something that is near and dear to my heart. As an engineer that focuses on suspension bridges, mostly the design of the repair and rehabilitation of suspension bridges. The bridge is special. I have I am quite fortunate and lucky to be able to say I've crawled over almost every inch of that bridge, whether it was doing a routine biennial inspection or whether it was what Jonathan alluded to, doing an internal cable investigation, removing suspender ropes. I'm very passionate about suspension bridges. Considering that I live in the New York area, and that bridge is an icon. While it's an icon worldwide, it's really an icon here in the New York City area. I'm quite proud to be able to say that I've worked on the bridge physically, and the opportunities that WSP and the bridge owner, the TBTA, have afforded to me. I feel myself very blessed to have that, to have the Verrazzano-Narrows Bridge on my resume of suspension bridges that I've worked on.
To me, the Verrazzano-Narrows is kind of a beacon to bridge engineers, almost like a call to, if you're able to, and have that opportunity to work on the bridge and reach back in time and to touch that engineering excellence and to give you inspiration to move forward. Especially if you have a relation to the Aman and Whitney legacy, it's almost like you're able to reach back and hear the voice of Othmar Aman, and it's pretty moving, I think, for us.
Is there anything important that you feel like we might have missed that you think would be a nice addition to this article that will be about the bridge and its anniversary and its contribution to bridge engineering?
Well, I think it would be interesting to mention WSP was part of a team that analyzed the seismic response of the bridge. And there was a subsection of that analysis that covered the New York City Marathon, basically to say, how would the marathon affect the Verrazzano-Narrows Bridge? And so that was analyzed. There was no real it was a new type of analysis that was considered, and nothing really needed to be done to the bridge, really, either for seismic or for the marathon.
So far, we've talked about the history of the bridge, everything from why it was built, why it was placed where it was placed, to the upcoming 60th anniversary. So that's all history. But what about the future? What are we looking at into the future? The future for the Verrazzano-Narrows Bridge is incredibly bright. The bridge has been maintained in a state of good repair, quite amicable, not amicable, quite admirably, in a fashion where you admire, by the TBTA. They've done a great job with maintenance on the bridge, which puts the bridge in an awesome position to be able to function into the indefinite future. One of the projects that the bridge owner is currently looking into is main cable dehumidification. When it comes to suspension bridges, almost any element of the bridge can be replaced. We've talked about suspender ropes, we've talked about stiffening trusses, superstructure, all of that can be replaced. It's extremely difficult to replace your towers, your anchorages, and your main cables. Your anchorages and your main cables typically are fairly straightforward to keep in good condition, but it's the main cable that has a lot of unknowns. The exterior of these main cables is nothing but a weatherproof covering. It's a painted wire that's wrapped around the main cable. But it's what's inside that, what you can't see on a day-to-day basis, those tens of thousands of individual wires that are in the cables that hold up the bridge that you can't regularly inspect. As Jonathan said, as WSP, we've done 2 rounds of internal inspection on the main cables. And while the cables are currently in good condition, the trick for the bridge owner is how to keep them in good condition. They're currently in the process of procuring the engineering services to do the design of a main cable dehumidification system. It soon will be let to construction to install that main cable dehumidification system. And Todd, main cable dehumidification is probably a topic that we could spend a whole nother hour on. But quite briefly, what it does is it's a system that puts dry air into the cable. By eliminating the moisture in the cable, you reduce the corrosion in the cable. Corrosion isn't the only item that can cause a cable to lose some of its strength, but it's certainly one of the easier ones to address and one of the more visible types of deterioration. So by eliminating the deterioration in the cable, aka rusting of the cable, and all of the nasty side effects that come with that, by stopping that corrosion, it, in essence, all other things being equal, it prolongs the life of the main cable indefinitely. And since that is one of the most difficult elements on the bridge to replace, if you can extend the life of your main cables nearly indefinitely, you extend the usefulness of the bridge almost indefinitely. So while 60 years is a great milestone, it's probably only a drop in the bucket for what the future of the Verrazzano-Narrows Bridge holds. And I certainly hope WSP is a part of that future.
I did want to say one innovative thing that we didn't talk about was the erection of the deck. So this was the first major suspension bridge to have the erection of the superstructure start at mid-main span and work back towards the towers. Previous suspension bridges where the superstructure was erected by starting at the towers and working towards the main span. And there's different reasons for both applications, which basically have to do with the force in the tower at the top and the bottom where it's a fixed connection to the tower anchor point, and the top where there's the saddle that the cable passes over. And so both those locations transmit stress or receive stress, and the different erection sequence allows for a transfer of loads from the cable to the towers that helps to reduce the complexity and the size of the towers if it's done properly. And since then, the major suspension bridges have followed that deck erection sequence of starting in mid-main span.